This is the cutout of my figure, and I've marked the center of mass. It's over in the x direction 1 unit, and down in the y direction not quite 1 unit, but minus 0.9. And I'm going to balance this on the flat edge of my pen or my pencil tip, like this. So I'm going to put the point of my pencil exactly right on that point, like this. If I've done this just right, it won't fall when I let go, because the force due to gravity acts right through that center of mass and is balanced by the equal and opposite upward force of the pen in exactly the same spot. And so the mass will not move. So that's a fun physical application of double integration. And this is a nice physical check of your calculations, because if you're off even by just a little bit, it won't work. For example, when I visually took a look at this figure and I tried to do a visual estimate of where I thought the center of mass ought to be, I really thought that it ought to be a little bit lower here at, say, 1 and minus 1. But all this extra mass out here is what pushes this center a little bit up from where you might think it ought to be. And so if I try to balance this figure right here a little bit lower, then what's going to happen is that the center of mass is to the right of my pencil tip, the way I'm holding it this way. And so it's a little bit too far to the right, which is going to make this want to fall this way, because the force due to gravity will pull it down through the center of mass in that direction, in this direction. So I'm going to put my pencil right there, a little bit to the left of the center of mass, and I'm going to let go. And which direction does it fall? To the right, because the center of mass was to the right of my pencil tip.